All right, welcome back to another edition of Honors Chemistry. How you guys doing today? Today we're going to be continuing to talk about, well, actually not continuing, we're just starting to talk about acids and bases. Whoa. We're going to be starting to talk about acids and bases. You guys should have completed a homework assignment already and turned that in, but let me just see who all is here today. I am having a little trouble on my own here getting the chat up. So I see 5 of you guys here, 7 of you guys here this morning. All right. So just say hi in the chat if you're here so I can know who all is here and all that kind of stuff. And you guys had a bit of a homework assignment. So first time recently looking in the book, all that kind of stuff. And let's see how you guys did. So the book, like I said before, is not my favorite, but it's okay. So, and when we don't have class together, the book is going to be useful, right? It's going to be better than nothing, right? It's going to be better than not having any kind of resource and just looking around on the internet hoping that you're getting accurate information. So the book is going to be accurate. It's just not always the best. All right. Athena is back. All right, good. So let's just jump right into this. Obviously, you guys probably have some questions about now, so I don't want to deal with all of your questions before I go through this. I'm going to go through the homework together, but I do want to say you guys should have already turned in your homework, okay? I am serious about the homework deadlines, so make sure you turn your homeworks in on time. And if you don't, I'm going to be taking points off. So make sure you turn your homeworks in on time. A lot of you guys probably wondering about the test. I have been having a lot of other stuff going on, such as I'm finishing up a video on the COVID-19 that I wanted to publish today or tomorrow, and also my baby's keeping me up a lot at night. And so because of those, I haven't had really much time at all to grade your tests. I will grade them by Thursday. And I know you probably will want them tomorrow, but it's not going to happen. So I will grade them by Thursday. So sorry that it's taken me a while. Maybe it's going to be really fast because maybe you guys all did really, really well, which is going to be great. And so, yeah, so if you guys have individual questions, then just email me and I will reply to your email even if I haven't yet. You know, again, I've got hundreds of emails, and so sorry if I don't reply immediately to emails and all that kind of stuff. I know I should be giving you guys priority, but there's a couple things that I do have going on that are taking up a lot of my time. So anyway, hopefully the book worked out. And today, let me just say this ahead of time before we finish up. You have a homework assignment for tomorrow, but the homework assignment, there's nothing for you to turn in. Does that mean do nothing? No. Okay, you guys are responsible, young adults, and I want you guys to look at the assignment that I give you guys on Google Classroom, and you guys are going to be just doing some reading through some things and watching a couple videos that are about logs and about log scales in science. That is, so just a little heads up, and I'll just write it over here on the side. Okay, so log scales in science, log scales in science, and log is very important in science. Okay, log scales in science. So obviously the pH scale, which is going to be the reason we're learning about logs, and also it's going to be talking about the Richter scale, which is for earthquakes, and then also the decibel scale, okay, which is for sound. And so these are probably 3 very important log scales in science. And so you guys are going to be reading some papers and watching some videos on them, not my own videos. In going through some of this stuff, I realized that there's really not a lot of good videos on some of this stuff, and so I probably need to make some videos on some of this stuff too. But anyway, yeah, so there are some videos that I want you guys to watch and some papers I want you guys to read about that stuff. But no homework, okay? So you might want to skip it, but don't, because we are going to be jumping right into logs and pH on Wednesday. And if you don't know anything about this background on logs, you're going to be lost. And I know that a lot of you guys in 10th grade haven't maybe even talked about logs in math yet, and that's why we're doing this. If you guys already were familiar with logs in math, then I wouldn't take a day to have you guys look at this stuff. But instead, because you guys don't know logs in math, make sure, at least from what I hear, unless you guys are off in advanced math or something like that, I want you guys to go through these videos and learn logs. So make sense of, well, what is a log? What is that log function? What's the purpose of the log function? How does it work? And all that kind of stuff. So very important. And if some of you guys are following some of the COVID-19 stuff online, you may even find that some of the graphs are logarithmic graphs. If you look at some of the growth graphs, they might be logarithmic in scale. So it's very, very important. You'll find these log scales all over the place. So we'll come back and talk about that more on Wednesday. I might have some time to finish up and talk about that some today, but I want to finish early. I want to finish by 10 o'clock because I do have a test that I'm giving in my next class, in chemistry class, okay? So without further ado, let's jump into the stuff that was from your reading, from the book and all that. So make sure that you've done your reading and you're looking at that and trying to answer some of these questions. And so some of these questions you guys should have probably answered. Some of them may have been confusing. And feel free in the comment section to stop me as I go if anything doesn't make sense. But let's not say, hey, Mr. Ketz, what's the answer to number 3? Because I'm going to go over all of it, okay? But as I go, if I don't explain enough, just stop me and say, you know, please explain that more. I don't get this part, or whatever. Okay, so Arrhenius. Arrhenius was one of the first guys that really did research on acids and bases and came up with a good definition. And really, sometimes his definition isn't really given credit because his definition is a little bit more complex than what is typically reported as. But let's just stick with what people normally think as Arrhenius acids. So an Arrhenius acid is going to be something that can give H plus to a solution. Okay? And an Arrhenius base is going to be something that can give OH minus to a solution. Okay? Technically speaking, Arrhenius said that an acid is going to increase the H3O plus or H plus concentration in a solution, and a base is going to increase the OH minus concentration in a solution. But this is kind of a simple answer that I'm going to stick with. Okay? Yeah, you can go ahead and send the assignment again after class, but again, it's going to be late, so make sure you turn it in on time. All right, so Arrhenius' definition is nice because we can look at a single chemical and define it as either an acid or a base, which is advantageous sometimes. All right, so we have 3 different definitions for acids and bases, and they're all useful. We're not going to say one is right and one is wrong. They're different perspectives, and each definition is useful. Okay, so an Arrhenius acid gives H plus to a solution, and you guys should have read that H plus, well, really doesn't, typically is not all by itself, right? Remember, hydrogen is just 1 proton and 1 electron, right? And so if H plus, that means it's really, H plus is just a proton, okay? And so acids typically are thought of as, you'll see the words protic, or things like that, because an H plus is simply a proton. Most hydrogen doesn't have any neutrons, and once the hydrogen has lost its electron, then H plus is just a proton, and that's it, 1 lonely proton. And so you can imagine that H plus is extremely reactive and is going to want to stick to things. Anything that has electrons is going to stick to, and it does. And you can see that in behavior of extremely acidic things. But when it's in water, this H plus is not going to exist as simply a proton. It's always going to stick to water. And if water's H2O, the way it's going to stick to water is going to be H3O plus. All right, and so we're going to use H plus and H3O plus interchangeably because H plus and H3O plus are the same thing. When an acid is dissolved in water, which most of the time we're going to be talking about aqueous solutions. So when an acid is dissolved in water, it's going to be always in this form. Actually, the form is a little bit more complex. That H plus is shared by multiple waters, but this is, good enough for our purposes. Okay, so most of the time that acid or that H plus is going to be in this form. All right. Now, I do realize that in answering number 1, I've neglected the stuff on top. So let me just mention there are some common acids that I want you to know, but you guys are lucky because we won't have any tests on these per se, because all your tests are open notes, right? And so if I ask you on a test, what's the formula of sulfuric acid? You could just look it up and write it down, obviously, okay? So I'm not going to test you on this, but I included this in the homework because I wanted you guys just to be familiar with these. All right, I'm going to say hydrochloric acid, and you should know it's HCl. I'll say nitric acid, and you should know HNO3. So there's only 5 of them, 5 common acids. Although you don't have to memorize them for a test, please do be familiar with these formulas, all right? And I do have a little Quizlet. Just go through the Quizlet one time, and that'll familiarize yourself with these acids, and that's about it. All right, so that's what an Arrhenius acid and a base is. All right. Now, down here, we're going to classify these as acids, bases, or neither, according to the Arrhenius definition. Arrhenius is really the only true definition that enables us to identify single chemicals as acids or bases. So let's look at each one. KOH. And these are fairly straightforward. If it has an OH at the end, it's going to be a base. Okay. Now the exception to these are going to be alcohols, so like your organic molecules that are alcohols, that have alcohols in them, but you're not going to see them. I'm not going to try to confuse you. So anything that you guys see that has hydroxide in it is going to be a base. And so it's got to have some metal and an OH here, or it could have NH4 plus and an OH here. Okay. So this OH right there tells us that it's a base. Okay. Next one, HNO2. Now, it's not one of these common acids, but it does have H in front. And if it has H in front, it's going to be an acid. Other things do have H in them. So, for example, you might see something, for example, like CH4, right? That's got 4 hydrogens, but that is not an acid. And without getting into the detail of why it's not an acid, we can simply say that hydrogen is not in the front. And if the hydrogen is not in the front, it's not going to be an acid. Anything that I will write and give you that is an Arrhenius acid will have an H in front. All right, and the only exception to that, it's not a true exception to that, but it's kind of like an exception to that, it's going to be water. Okay, and what do I mean? Water is one of those strange things that has H in front, but it's actually not really an Arrhenius acid. Water can function as an acid. It can function as a Bronsted-Lowry acid, but really water is neither, according to the Arrhenius definition, because if I put water in water, it's not going to increase the amount of H plus you have in the solution. Okay, so H2O is the only thing that has H in front and is not an acid, at least as far as things that you'll see from me. Okay, and in order to be an acid, it does have to have the H in front. So when we go over to C and we see, once again, H in front, that is also an acid. Okay, so that's potassium hydroxide. This is nitrous acid, not nitric. Nitric acid has 3 oxygens. Nitrous acid has 2 oxygens, and this is hydrobromic acid. Just like hydrochloric acid is HCl, this is hydrobromic acid, HBr. Now KBr over here, it's got no H, it's got no OH, so this is going to be neither. So water is neither, and your salts, so any kind of just simple ionic compound without H or OH is going to be neither. Last of all, we have barium hydroxide. Hydroxides is going to be a base. So those things are fairly straightforward. Your Bronsted-Lowry, I'm sorry, your Lewis, or your Arrhenius acids and bases are fairly straightforward. We can look at the chemical and tell H in front acids, OH in the back it's going to be a base. Now, the book, I believe, mentions this briefly, ionization and dissociation. It talks about how typically your bases are dissociating and your ions, or your acids are ionizing. So let me just go ahead and write down, let's write down these equations and then come back to the definition and see what's going on. So there are two different possibilities that you could have written for this one. So the ionization of H2SO4 in water, you can write H2, well actually there's a lot of different possibilities. H2SO4, we can write it plus H2O, and we can make this HSO4 minus plus H3O plus. You can write this as H2SO4 plus 2H2O makes SO4 2 minus plus 2H3O plus. So either one of these is going to be fine. This is going to be a single ionization. This is going to be a double ionization. Or if you really wanted to, you could remove the water and just have H plus over here. But this is a more proper way to do it, the way I've done it with something plus H2O. Okay? And let's just move this up a little bit here. Ooh, there we go. All right. So either one of these is going to be an ionization of H2SO4 in water. And so here we go. Let's just do the dissociation of MgOH in water. So magnesium hydroxide. And it's not very soluble. Remember, according to your solubility rules, hydroxides are insoluble except for alkali metals and NH4 plus. And this is neither. Right? So it's not very soluble, but you can dissolve a little bit in water. So magnesium hydroxide, when it dissociates in water, it's going to be Mg2 plus 2 OH minus. And it's important that you recognize that this subscript here turns into a coefficient over here on this side. So when we look at these two different things, we notice that there is a difference. Okay? The magnesium hydroxide is already an ionic compound. Magnesium hydroxide, we already know, right? Metal and polyatomic ion. So this is an ionic compound. And ionic compounds are already composed of ions. So when it dissolves in water, it's going to just simply dissociate or break up into its ions. And we've already learned about that. That's normal. Ionization is new to us. We haven't talked about ionization ever before, right? And what's going on? Because H2SO4 is not ionic, it's covalent. Okay? If you look at H2SO4, we got non-metal, non-metal, non-metal. They're all non-metals. And this is a molecule, so it is a covalent compound. H2SO4 is covalent. So when you dissolve it in water, what it does, it literally reacts with the water, and then it turns into ions. So the ionization is for covalent things, and it's a chemical reaction where that covalent thing is literally splitting up into ions. But for an ionic compound, it's merely dissociating. It's just splitting up into its separate ions. Okay? So that's the difference between ionization and dissociation. Ionization being for covalent things, dissociation being for ionic things, and it's simply ionic things splitting into ions, and covalent things, the ionization is reacting with water to form ions. Okay? So stop me if you guys have any questions as we go. That is your Arrhenius acids. Now you guys have this term polyprotic acid, which you guys probably, and we've talked about polymers before, and you've probably talked about this in math class before. Poly is a term that means many, right? And so, and the protic, which I just mentioned before, has to do with the fact that, remember, your acids are protic because your H plus is essentially a proton. And so polyprotic acids are many H pluses, okay? So any polyprotic acid has more than one. I know 2 doesn't really sound like many, but it's going to be more than 1 H. And it's not simply an H, but it's an ionizable H. It's possible, for example, especially for organic compounds, to have a whole bunch of H's that are not ionizable. And I will always make sure to write the ionizable H's out in front, all right? For example, and your book doesn't always do this, so it might get a little confusing. Let's see, acetic acid, right? Acetic acid has this structure, right, where C, CH3, O, O, H, okay? And it has 4 H's on it, but only one of them is ionizable. And so the way I'm going to write acetic acid for you guys is H, C2, O, no, C2, H3, O2. Okay, so I'm going to put an H out here in front so that you guys know that that acetic acid has 1 ionizable hydrogen, but it has 3 over here, 3 non-ionizable hydrogens. And so you'll find that sometimes you'll see some acids that are a little bit confusing. They might look like they're polyprotic, but they're really not. Acetic acid is not a polyprotic acid. And that's true mainly for your organic acids, not so much for your inorganic acids or your, yeah. So here we go. So that, you're going to look up at the H's out here in front. And so next up, number 7, it says, identify all the common acids listed at the top of the page that are as monoprotic, diprotic, or triprotic. And we can just, I'm not even going to write this down. We can just go over them together here. And you guys should have had this written down. But all we do is we just look at the H in front. Okay, so there's 1 H in front. So hydrochloric acid is monoprotic. Sulfuric acid is diprotic because we got 2 hydrogens there. Nitric acid is monoprotic. Phosphoric acid is triprotic. And carbonic acid is diprotic. Okay, so mono being 1, right here, monoprotic being 1, diprotic being 2, triprotic being 3, however many H's you have in front. So that's your Arrhenius acids, always dealing with looking at the particular chemical and seeing how many H's it has. Okay, so any questions about Arrhenius acids? Are you guys all still with me? I see 13 of you. Let me say 13 of you guys with me. Some of you guys not with me. So, again, I'm going to have to split out early, so I'm not going to be able to take time to talk about logs. We'll talk about them on Wednesday. But I do want to finish out this homework assignment for you guys. So, what's a Bronsted-Lowry acid? What's a Bronsted-Lowry base? And simple definition here. So your Bronsted-Lowry acid is going to be very similar, H plus donor, right? So still looking at that in terms of H pluses. And the Bronsted-Lowry base is going to be an H plus acceptor. But the main difference is not so much the definition of the base, but the main difference in definitions is the Bronsted-Lowry acid base always looked at them in coming in pairs, okay? And so they said that these things, in order to have an acid-base reaction, you have to have both. There's an acid and a base. There's a donor and an acceptor. So one chemical itself is not necessarily an acid or a base, but it depends on how it reacts in a particular chemical reaction. And in fact, one chemical might be an acid when combined with other chemicals, but might be a base when combined with something else. So, that's why it's impossible to identify a single chemical as an acid or a base, because we don't just look at the chemical formula, we look at how it reacts with other things. And so we need to know what it's paired with. There's no one single chemical that is a Bronsted-Lowry acid. It has to be how it behaves in a chemical reaction. And number 10 is really, really important for you guys to understand and to follow. at first, this might be difficult, and I understand that. At first, this is probably going to be maybe the hardest problem in the whole homework that I assigned you guys, but it's super, super important. So make sure that you look at this carefully, and we're going to go through all of them in number 10. All right, so the Bronsted-Lowry acid and base, the acid is the one that is giving the H+, and the base is the one that's accepting the H+. So our first problem is relatively easy, but some of the other ones might be a little trickier, and I'll give you guys even trickier ones later. So we can see right away, okay, we're thinking, okay, that's acid and that's base. Why? Because that has an OH and that has an H, and that makes sense, right? And that's exactly what's going to happen. Let's even get a couple different colors here. We'll do red for the acid. So this is going to be our acid, and this is going to be our base. But I wouldn't necessarily know it just by looking at the chemicals. I need to see what happens over here. So I need to follow this Br, right? And so when I follow the Br, so I'm always going to be looking at this thing over here. So when I follow the Br and I find it over here, I notice that the HBr has lost its H, right? It's lost its H. And so that must be meaning that the HBr is acting as an acid because it's lost its H. And when it goes over here, and so this is a pair here, when it goes over here and loses its H, that means it's turned into its conjugate base, okay? So the acid, when it loses its H, turns into its conjugate base. Well, why would we call this a base and not a conjugate acid? Simply because it's the opposite of this. It's when it loses an H, it now has the ability, if it were to go in reverse, to accept an H. And so if it's going from right to left and accepting an H, this would be acting as a base. Remember, acids are H+ donors and bases are H+ acceptors. So going from left to right, this Br is acting as an acid because it's losing an H. Going from right to left, this KBr is gaining an H, right? And therefore is acting as a base. So this is an acid conjugate base pair, okay? The potassium is really doing nothing at all. You could literally ignore the potassium. It's doing nothing at all. Okay, so this is the base. Why? Because it's accepting the H. And how can we see that? We see the OH here turns into H2O. So the OH has gained an H, right? And so this H2O is the conjugate acid of OH minus. So this is OH minus acting as a base, gaining an H plus and turning into the conjugate acid. So going from left to right, this is gaining an H. Going from right over to left, this is losing an H plus. That's why this is a conjugate acid. Okay? And it probably would make a little bit more sense if we just forgot about the K. So let's even rewrite that. It might make a little bit more sense to ignore that. So let me just rewrite this. I know we're gonna run out of time, but it's useful. So remember your ionic compounds, they just dissociate. So we say OH minus plus HBr. That's not ionic, so we're gonna write the whole thing. Goes to Br minus plus H2O. When you remove the potassium, things start to be a little bit more obvious, okay? So the OH minus going from here to here is gaining an H. And so this is going to be your base, but the H2O, if I went from right to left, would lose an H, okay? The HBr, right here, going from left to right is losing an H. And so therefore it's acting as an acid, all right? And the Br minus, if it were to go from right to left, it would gain an H and therefore it would be a conjugate base. So your conjugates are all on the right side, all right? And they're always going to be working this way. So pay attention to this reaction that I have up here. and go back to this. That's going to be your go-to thing to, what in the world is an acid, a base? What's this conjugate acid base? And come back to here. Look at what we've done by removing the potassium and look at what's going on there. Okay. So down here we have, this is a nice one. I like this one a lot because we have sulfuric acid reacting with nitric acid. Uh-oh, Mr. Ketz, they're both acids. So which one's your base? So this time we actually have to look at the reaction to see what's going on. I like this one. I'm going to probably put something like this on the test. Who knows? So what's going on here? We have H2SO4 and HNO3, and we look over here and say, okay, this SO4 and the SO4. So follow that, the SO4 and the SO4, which means the H2SO4 has lost an H. And if the H2SO4 is lost an H, this is going to be acting as an acid, right? And this is going to be your conjugate base. The conjugate base is the acid after it's lost H+. Okay? And your HNO3, although it's an Arrhenius acid, in this case, what's it doing? Your HNO3 here is turning into H2NO3+. Here it has gained an H. And so this is a base. It's acting as an H+ acceptor, and this is going to be your conjugate acid. Okay? The conjugate acid is the base after it has accepted an H. So sometimes, things it might look like, they're both Arrhenius acids, but when reacting together, and this is a real chemical reaction, okay? This is a useful chemical reaction at that. Sometimes, your acids can react with each other, and the stronger acid can actually act as the acid, where the weaker acid is going to act as the base. Okay? Next up, down here. So we have something strange looking going on here because we don't have an OH minus, but instead we have an oxide, which oxides are even more powerful bases. And so what do we have? We have, this is phosphoric acid, which is going from H3PO4 to Na3PO4. Again, we can literally ignore that sodium, okay, to see what's going on. Literally, this thing is losing a whole bunch, losing all three of its H's. And so this is going to be our conjugate base, okay? And here we have this must be our base. And what is it doing? The base is what? In this case, that sodium oxide, the base is O2 minus, okay? And so O2 minus can gain not one but two hydrogens and turn into H2O. So it's going to act similar to hydroxide, but it's going to be even stronger. It's going to have the ability, because it's an oxide, it's going to have the ability to take up two hydrogens going from here to here. So this is the base, and then this, therefore, is the conjugate acid. Okay? And let me go through a couple of these a little bit faster here. So what's going on here, this hydroxide, and this is, it's a little bit easier to look at the carbonate. So this is carbonic acid, the CO3. It's losing both of its H pluses, and so this is going to be our acid. This is going to be our conjugate base. The OH minus is doing what? The OH minus is acting as a proton acceptor. So here's our base. The OH minus is turning into H2O, so this is our conjugate acid. Okay? This one is the trickiest one in the whole page, maybe, although the one down below. So because we have lithium hydride. What in the world is lithium hydride? That is tricky because it's Li plus and H minus. Not H plus, but H minus. And we know that because the lithium must be a positive one charge. So the hydrogen has to have a minus one charge. Hydrogen can be plus or minus. And when it's minus, it's actually going to be a super strong base. And so if we look closely at what's going on, lithium hydroxide is doing what? Lithium hydroxide is actually losing an H. And so this hydroxide, this lithium hydroxide, this Arrhenius base here is actually going to be losing an H. And so in this case, it's acting as an acid. right? And so over here, this lithium oxide is going to be your conjugate base, okay? And the lithium hydride, because that's an H minus, well, what's going on? The H minus is gaining an H plus. So if you have H minus plus H plus, they come together and you end up with H bonding with H, or H2. So this is going to be your base. And once that H minus has accepted an H plus, it turns into hydrogen, which is going to be your conjugate acid. Okay? So kind of tricky there. The next one I don't think is as bad. So the next one, NH3 and H2O. The NH3 turns into NH4 plus, so the NH3 is receiving an H plus, and so the NH3 must be acting as a base. This is going to be your conjugate acid. Your H2O is doing what? Your H2O must be giving an H plus to NH3, and so that H2O in that case is acting as an acid, and when the water loses an H plus, it turns into OH minus, so this is going to be your conjugate base. Okay? So, over here, last one, all right, NH3, so your NH3 here, and your lithium hydride. Once again, anytime you see lithium hydride, you're thinking that's going to be a super strong base, and let's confirm, H minus going to H2, and the easiest way to look at this problem actually is to follow the nitrogen. So it's NH3, and here is NH2. So this nitrogen must have lost a hydrogen. So in this case, the NH3 is acting as an acid, and over here is turning into a conjugate base. Okay? So when you're losing, so the acid is losing an H plus, turning into its conjugate base, and that means this lithium hydride, once again, is doing this kind of crazy stuff over here. So the H minus is your base, and your H2 is your conjugate acid. So I got to wrap it up because I got a test next block, and so we'll talk about Lewis acids and bases later. I'm going to wrap it up by answering number 11 real quick. Amphoteric means it can act as either an acid or a base, right? Can act as an acid or a base, and it depends on the particular chemical reaction. And so let's just look up on there. So water can act as an acid or a base, and back up here and look at NH3. Here it's acting as a base, here it's acting as an acid. In order to act as an acid or base, it has to be able to receive H pluses and donate H pluses. Also, we'll notice things like, here it is, your nitric acid can act as an acid or a base. Here it's acting as a base. So question, wait, I have a question. Why does H2O become OH minus? Because in this problem, your H2O is giving an H plus to NH3, okay? And when it gives an H plus to NH3, it must turn into OH minus because it's losing an H plus. When you lose something positively charged, you become negatively charged, okay? So here's H2O giving its H plus to NH3 and turning into OH minus, okay? We will talk, it's actually not being reduced. There's no redox going on here. There's nothing that's losing or gaining electrons in any of these problems. So no reduction, crazy. We will talk about this again tomorrow. We'll pick up here where we left off, and we'll talk about calculating pH. Make sure you read about logs, listen about logs, Richter scale, your whole decibel scale, all that kind of stuff, log scales. All right, so let's go ahead and close out here, and we'll talk about the rest of this stuff on Wednesday. See you guys, and thank you guys so much for being here.